Alright, hello class. This is video lesson 2, 4.4, part 1, but video B. Alright, so we're starting into applications of exponentials, base E, exponential growth, exponential decay. So in this case, and bear with my handwriting, and for some reason I couldn't make the font on this any bigger. I don't know why. The program I'm using just wouldn't, for this particular problem, wouldn't let the font go bigger. I will try to write everything down and say everything out loud so that you can see it. Or hopefully you've printed off this set of notes and they're sitting in front of you and you can read it as we're going through it together online. Alright, so in this case we're given televisions found that the monthly demand for its newest line of Blu-ray players, alright, so we're given the demand for Blu-ray players after T months, so time is in months. So the demand equation is 400 minus 4,000, minus 300 e to the negative 0.06t, where time has to be positive. Alright, solve the following. And so these are application types that tend to show up that we'll have on homework, and you'll have probably something like this on a test. And a final exam, they usually have something like this in the show your work portion of the final exam, where they'll give you an exponential function and ask you 3 or 4 questions based on it. Alright, similar to this example and the next one we're going to do in this set of notes. Alright, question A. What is the monthly demand for players after 8 months have gone by? So this is just plug it in and solve. So part A is find the demand after 8 months. So take 8, plug it into that demand equation, right, and then simplify. Now, when we're doing applications, keep in mind that you always need to, if it doesn't tell you where to round, just round that makes sense. We're going to get Blu-ray players, and we don't want a fraction of a Blu-ray player. So when you type this in, it comes out 2,143.6, right? I don't want a 0.6 of a Blu-ray player, not a whole one, so just round correctly. So 2,144 is what it would round to, and then it's an application, meaning that 2,000 has meaning, has context. And so always put units with your answer. That 2,144 is not just a number. It stands for Blu-ray players. So make sure you include the units. Always include the units. Alright, so that is the demand for Blu-ray players. So that answers the question. That's the demand for Blu-ray players after 8 months. About 2,144. Alright, the second question. In what month? So we're looking for time, right? In what month is asking for time? Did the demand equal 3,300? And so I'm going to write down my demand because it's no longer on my page. So bear with me while I write it down. Alright, so we've got our demand equation, and we want to know when that demand equation is equal to 333 and solve for time. So we're going to set the demand equal to 333 and solve for our t, solve for time. And so we did these. We practiced these before we went on break in the review. Isolate the e term, so solve for e first. So move the 4,000 to the other side by subtracting. So you're going to get negative 7,000 equals negative 3,000 e to the negative 0.6 times time. Divide by that negative 3,000 in front of the e term. Alright, so that simplifies. On this side I'm left with the e to the negative 0.6 times time. On this side, leave the fraction exact. So either leave it 7,000 divided by 3,000 or reduce it to 7 over 30, but do not approximate. Do not round until the problem is over, because my next step is to use a logarithm, and if you round, you're going to be significantly off. So do not round, leave it exact. Fraction, 7 over 30, or if you wanted to, you could leave it 700 over 3,000. Because the next step is to take the natural log. So I unbury, I get rid of, again, natural log and the e, are opposites or inverses. They undo one another and will leave me with the time part. And so I'm going to go up here. It's the natural log of our 7 over 30 equals that negative 0.06 times time, and then solve for time. So divide by that number in front of time. And so this is what we're going to plug into the calculator. Since time can be fractions. So I'm just going to rule of thumb, round a couple decimal places if I can. If the fractions are okay, and with time we can have a fraction of an hour, right? Time is in hours, or months, fraction of a month. We can have that. And so it comes out, if you type it into the calculator, 24.25. And remember, always include units. Our time is in months, so 24 1/4 months, the demand will reach 3,300. All right, the next question. How fast was the demand changing in a year? All right, so there's two parts to this. First of all, the how fast. Well, the how fast is a speed, rate of change. All right, how fast is it changing in a year? So that's asking you for the derivative, right? Want to find the derivative of the demand after 1 year. But remember, time is in months, so that 1 year really means 12 months. So make sure you're careful. We don't want to plug 1 in. If I plugged 1 in, then it'd be the rate of demand in 1 month. I'm going to plug 12 in because I want to know the demand in a year. All right, so find the demand, plug in our 12 months, our 1 year later. All right, so find the derivative of the demand. So again, I'm going to write my demand equation down so that I have it to look at. All right, derivative of the demand. Well, the 4,000 is just a constant. It will zero out, so that's gone. Derivative of the exponential, chain rule will be involved because there's something other than t inside. But the first thing you do is remember, derivative of the e is the e term. So write the 3,000 e to the negative 0.06 times time. But remember, we're not done yet. That's just the outside. We have to times the derivative of the inside. So remember, multiply by that negative 0.06. That's the derivative of the inside function. I'm going to simplify that before I use it. All right, I can take my negative 0.06 times my negative 3,000, so it's going to come out positive 180 e to that negative 6 times time, and then I'll plug my 12 months in, my year, 12 months. All right, it comes out 87.6, but remember, we're talking Blu-ray players, so I'm going to round up to the 88. And so don't leave your answer 88. That's not proper, right? 88 has context, and we want to answer the question, how fast? What's the speed of the demand after a year? And so after a year, the demand is increasing, right, because it's positive, by about, since I rounded, 88 Blu-ray players per month. All right, don't forget the per month. That's the units on it, right? Derivative is a rate of change, right? Like miles per hour, change in distance over change in time. This is change in demand, Blu-ray players, over change in time, months. Blu-ray players per month is my unit. So 88, so it's increasing by 88 so that's the speed, how fast. It's increasing by 88 Blu-ray players per month. All right, D. All right, we're looking for question D here. All right, this is kind of a throwback question. Average rate of change. All right, we want to calculate the average rate of change for the monthly demand between 20 and 30 months. All right, so average rate of change we haven't talked about much since chapter 2. All right, so it's been a little while since we've done it. Chapter 2 was a little while ago. But a lot of times we like to ask this question here, again, because, again, it's been a while since we've talked about it, and it's an important concept. So often we'll ask this on this portion of the test, and sometimes on the final exam, if it's an exponential type, this is where they'll ask average rate of change. All right, so average rate of change, remember, is the slope of the secant line. All right, so I don't need my derivative. It's just the change in my function. So change in the demand over the change in the time, right? Like our average speed, change in distance over the change in time. Same thing here. Change in my function, which is the demand, over the change in time. And the change we're looking for is between the 20th and the 30th months. And so those are the values we're going to plug in. So I'm going to find the demand. We usually plug in the bigger value first. So demand at 30 minus the demand at 20 over 30 minus 20. So there's my change in demand, the 30 minus 20 in the demand equation, over the change in time, right? The time is from the 30th month to the 20th month. And we plug those values in. So again, I'm going to find the demand by plugging them in my demand equation. All right, so to simplify that, first of all, I'm going to simplify my divisor. 30 minus 20, I can write, those are 10 months. So over the 10 months, specifically though, going from 20 to 30, that 10-month set, the change in demand is what we're averaging. All right, so we plug these into the original equation, not the derivative. All right, so no derivative involved, just the original. So I'm plugging them into this 4,000 minus the 3,000 in the E term. All right, so when I plug 30 in, I'm going to round to the whole player. I'm going to get 3,504 at 30 and 3,096 at 20. All right, simplify that. Make sure you're careful. Subtract and then divide by 10. I'm going to round to the whole number, so it rounds to 41. And again, don't leave your answer 41. It's application. 41 has context. So 41 is the average rate of change, right? Average speed for the change in demand over the change in time. And so on average, the demand is increasing by, again, I rounded, 41 Blu-ray players per month. All right, so on average, between 20 and 30, between those months, over that 10-month period, the demand for the Blu-ray players was increasing by about 41 Blu-ray players per month. On average, again, just an average. All right, the second question we're going to look at in this set of notes, again, very similar to the last one. This is, again, typically the types of questions we like to ask. As it turns out, we're actually going to be talking about YouTube, right, as we're using that medium to go over it. All right, so broadband internet's been growing way popular. It's exponential growth, right? More and more people are getting online. More and more people are posting videos. All right, YouTube and other services have been just exploding. All right, so a study was done between the years 2007 to 2013. All right, so over those years, where 2007 would be times 0. Right, 2013 would be times 6, right? 6 years after 2007. So our domain is just 0 to 6. All of our answers for time should be between 0 and 6, year 2007 to 2013. All right, we are looking at the N of T, which estimates the number of online video viewers in millions. So I've got to keep in track of the fact that when I write my units, right, the viewership is in millions, right? Millions of people. And that's, again, important to include in the answer. All right, be sure to label all of your answers with appropriate units. Give your final answer in the blank solution sets, in the blank spaces provided, if I can spit that out. All right, so again, very similar to how I'll word them on the test, the homework, and the final exam if this type of question is asked. All right, first one, estimate to the whole number. So I'm going to round to the whole number, the number of online video viewers in the year 2010. So 2010 would be time 3, right? I don't plug 2010 into my equation, I plug 3 in. So I take my equation, N of T, plug 3 in for T, so it's 35e raised to the 0.07 times 3. Round to the whole number because they told me to round to the whole number, and so it comes out 167.55, so that rounds to 167. Remember, that is not how we leave the answer. It's an application. That 167 has context. All right, first of all, it's in millions. So instead of 167 viewers, it's 167 million. And that's, again, important, right? 167 is a lot different than 167 million online viewers. Or you could just say million viewers. That would be fine, too. All right, so there's the answer to that one. So in 2010... about 167 million online viewers. All right, find and simplify the derivative. All right, and give the units. So find the derivative, simplify it, and give the units. So I'm going to write my equation down over here first so I can look at it. So 135 e to the 0.07 times time. All right, so derivative is, again, first thing you do is write down the original function. 135 e to the 0.07 times time, but then we're not done. All right, that's the chain rule, derivative of the outside times the derivative of the inside, and so you've got to remember the times 0.07. All right, then simplifying, the only thing you can simplify is you can take the 0.07 times the 135, and when you do, that comes out to 9.45 times the term. All right, and there is my derivative, and then the units. So remember, units are the change in my function over the change in the variable, or change in time in this case. And so my function represents millions of online viewers, and so that's the change in the function, millions of online viewers. Or you could do millions of viewers would be fine, but we're not done, that's not it. It's the change, like miles per hour. It's millions of online viewers per, well, our time period, which is years. All right, so millions of online viewers per year. Or like I said, you could shorten that to millions of viewers per year would be acceptable too. All right, the next one actually gives you the units. All right, nope, that's not the next one. The one after that gives you the units. All right, so C first and then D. All right, C then is asking you to use your derivative. At what rate, right? So that's the derivative. Are the number of online videos changing in 2010? Round your answer to the whole number. So this is just asking you to take your derivative and plug your time in. Since it's 2010, it's 3 years into our study. So n prime of 3 is you plug it into our derivative and then round to the whole number and then units. All right, so it comes out 11.67, so I'm going to round to 12. Don't just leave 12, otherwise you'll get points off. It's 12 million viewers per year. 12 million viewers per year is how fast it was increasing. All right, so that's the rate of increase. All right, in 2010. All right, the next question. In what year? So we're asking for a time, right? In what year was the number of online videos increasing at a rate of 2.5 million online viewers per year? So there's my units on my rate of change, right? Million online viewers per year. Round to the whole number. And so this one's asking you to find a time when the rate, which is my derivative, was 12.5. Alright, so I'm going to take my derivative, set it equal to 12.5, and solve for time. Now, just bearing in mind my previous answer was 12, and so I'm going to guess it's either going to be sometime in 2010 or maybe 2011. As it shouldn't be too far away from the previous answer since it's 12.5. Alright, so take my 12.5, set it equal to my derivative. So remember my derivative was 9.45. E to the 0.07 times time. All right, and solve for time. First step, divide out by that 9.45. All right, and so remember, we're going to leave the fraction. We don't want to round it, and so you can type it in your calculator and get out a slightly nicer looking fraction. I'm going to just leave it. 12.5 divided by the 9.45 equals the E term, E to the 0.07. Take the natural log of both sides, so natural log of that fraction, where we left the fraction exact. Remember, leave exact. You can read that. Good luck. It says leave exact. Do not round this fraction. Natural log of it, so I'm just going to leave it, equals the natural log of the other side. Again, we take the natural log, get rid of the term, and so that's going to equal 0.07 on this side. That's still the natural log of that fun fraction. Okay, and then the next step, divide by 0.07. So again, I'm going to take the natural log of 12.5 divided by 0.95, 9.45. Again, that's going to go in first, and then that whole thing divided by our 0.7. So again, type this in the calculator carefully. All right, time's going to come out. It comes out 3.99, so I'm going to round to 4. All right, so in what year? Well, it's 4 years after 2007, all right, which is in 2011, right? 2011 is 4 years after 2007. All right, so the answer is in 2011. All right, the last one for this set of notes. All right, so the last one, again, is a throwback question. It's asking for average rate of change between the years 2010 to 2013. So 2010 would be time 3. 2013 would be times 6, and so it's looking for our average rate of change, ARC, average rate of change. Remember, that's the change in our function, right, which are number of online videos, over the change in t, which is time. Alright, so I'm going to write my original function here because that's what I'm going to use. The original function was 135 e to the 0.0 times time. Alright, that's the one I'm going to use. I don't use a derivative when I'm finding average rate. Just instant rate is derivative. Average is the change of the original function over the change in the time. Alright, so the original function, I'm going to plug 6 in, subtract plugging 3 in, and then I'm changing time as 6 minus 3. Alright, so change in time, change in my function. Alright, so 6 minus 3 is going to give me a divide by 3. We plug those into my original, and I'm going to just round a couple decimal places. So when I plug them in, when I plug in 6, I get 205.46. When I plug in 3, I get the 166.55. And then just solve that. And make sure you're careful. Divide after you subtract. Alright, comes out to 12.97. I'm going to round up to 13. And again, remember, 13 is not your final answer. Alright, your answer should include units. So the average rate of change is 13 million online viewers per year. Alright, so again, million viewers per year would also be acceptable. Alright, so we're going to stop there. That's going to be the last problem we're going to look at in this set of notes. The next set of notes will be 4.4 part 2, which will get into exponential growth and decay models. Alright, and so that's the next set of notes that we will go over. And so we're going to wrap that up there.